Thank you very much for the invitation and the great conference. So today I'll be telling you about the evaporation history of charged black holes. This is work together with Adam Brown, Jeff Pennington, and Michel Chatuk, who's here in the audience. So the setup is extremely simple. Consider a charged black hole without any surrounding matter that is just described by two parameters, its mass m and its charge q. And my goal for the talk today is to describe how such black holes evolve as a function of time due to Hawking radiation in the MQ plane. This problem might seem quite boring and old school at first sight, so let me give you a spoiler so that all of you don't leave the room. So when starting at a very large charge, so very much on the right-hand side, and I'll quantify what that means in a second, quantum gravity corrections are critical to describe the evaporation history of this black hole. So in order to describe the trajectory of this black hole, we'll have to understand both perturbative and some non-perturbative effects in gravity. So for neutral particles, it turns out that perturbative effects will be important. So this is, for instance, for photons or gravitons in our own universe. And for charged particles like electrons or positrons, it turns out that a combination of perturbative and non-perturbative effects need to be understood. And the way that we'll understand them is from the string equation in a minimal string model. So there's no stringy corrections for these black holes, but in order to understand the non-perturbative effects that are important for electrons, it turns out that we'll rely on some techniques from string theory. So in order to tell you why quantum gravity are important, let me do back of the envelope calculation. So for neutral particles, they don't carry any charge, so they drive black holes towards extremality, wherever you are in this plane. And for any particle that we know, let's say it's massless, the energy loss of a black hole with time is given by the temperature of the black hole to some power, which is given by the difference between the mass and the charge above extremality, also to some power. I'll quantify what these powers are in a few slides. However, for charged particles, if charged particles satisfy the weak gravity conjecture, they drive black holes away from extremality, at least naively. If these particles satisfy this bound, it turns out that they get emitted through a process called Schwinger pair production, which is a non-perturbative process in quantum field theory on a curved background. And let's just take the formula of Schwinger pair production for Wikipedia, which is given in terms of the mass of the electron, the charge, and the electric field. And let's imagine that we just take the electric field to be the electric field of the black hole at the horizon. So you get this formula, which I rewrote in this fashion. So when Q is big enough, you see that the pair production rate is extremely suppressed. However, this formula is a bit deceiving because, as I'm sure most of you know, the ratio between the mass of the electron and the charge of the electron in our known universe is immensely small. So big Q really has to be very large. So to tell you exactly how large it needs to be such that no charged particles get emitted and the black hole is driven towards extremality, it turns out that these numbers are relevant. The black hole needs to have a charge bigger than 10 to the 44 and a mass bigger than 10 to the 6 solar masses. So if I start to the right of these lines, the black hole will just approach extremality. How close will it get to it? Just balancing the loss of neutral particles to the loss for charged particles, you get the following formula that it gets to a mass that is exponentially close to extremality. So we get exponentially close to this line. However, this calculation suffers from problems both for neutral and charged radiation as we approach extremality, and that's because in recent years we've discovered that quantum effects are important in that regime. And the purpose of the talk today will be to understand that better. So let me just review what are the signatures of the fact that quantum corrections become important. So for a neutral particle, these authors already in the 90s noticed that there is a breakdown of semi-classical thermodynamics for near-extremal black holes. So the way to see this is to look at the energy above extremality as a function of the temperature. If I emit a single Hawking photon, if it's thermal, it has its energy approximate to the temperature. However, the energy, if you do a little calculation, the energy that these black holes have above extremality goes quadratic with the temperature. So, namely, there's a regime where these two lines intersect that is given by this energy scale, the breakdown scale, which for charged black holes in our own universe behaves like 1 over the cubed charge of the black hole. So, right as we approach these intersection, if I emit even a single Hawking quantum, the black hole, the black hole geometry completely changes because I can get much closer to extremality. And if my black hole somehow lands in this region, the geometry, this process of radiation even stops making sense, because if I truly emit a photon or a particle with this temperature, I would go below extremality. So something must go wrong with the calculation. So as I said, the emission of even a single neutral particle changes the black hole drastically. What about for charged particles that were emitted through Schwinger pair production? Well, there was a problem there too with my previous calculation. Namely, the Schwinger pair production rate that you typically compute is a production rate per unit time per unit volume, right? Actually, as we approach extremality, the near horizon geometry of a black hole develops an infinitely long throat whose geometry is AdS2 times S2. And this geometry actually has a divergent volume. So in principle, the non-perturbative calculation that I showed earlier should be multiplied by the volume of a spatial slice, and actually that computation that I showed earlier should be quite robust because the electric field is actually constant along this space. So it should be multiplied by the volume of a spatial slice, which is infinity, so naively that suggests that the pair production rate is infinite as the temperature goes to 0. Let me just present what we've discovered in recent years as we've approached extremality. That's unrelated to these particles, but these effects should somehow be incorporated in the back of the envelope calculations that I showed previously. So in recent years, we've discovered that the resolution for this thermodynamic breakdown comes from perturbative quantum gravity effects. So let's start with a purely extremal black hole, which, as I said, has an AdS2 times S2 near horizon geometry, and perturb the action by all possible modes of the fields. So in particular, there are some modes of the metric that Sen and collaborators discovered in the 2000s that turned out to be 0 modes of the action. So if I expand the action, the Einstein-Maxwell action, to quadratic or even higher order, these modes leave the action completely unchanged. And what these modes are is that there are large diffeomorphisms of the near horizon region, which change the way in which the infinite throat is glued to asymptotic infinity. Now, these modes in principle give you a divergence. There are 0 modes, so they in principle give you a divergence exactly at extremality, so we need to somehow regulate them. And one way to understand them is to take the extremal metric and perturb it a little bit away from extremality, so change the classical background around which we're doing the determinant calculation. So now this metric is the near extremal metric, and we can take the same modes and analyze metric fluctuations with the same modes. And what turns out to happen is that this correction of the metric gives a non-zero weight to the 0 modes that were present at 0 temperature. So now we have, at low temperature, a very strongly coupled set of modes. And these modes turn out to be precisely the modes that people study in 2-dimensional toy models, namely in JT gravity. But you could actually see it without ever doing the computation in 2 dimensions. You would just do an expansion of the 4D metric for the specific set of modes. And you find that the Einstein-Maxwell action takes this form at quadratic order. Here, epsilon just parameterized specific zero mode fluctuations. They're just the amplitudes of these fluctuations. And you find this quadratic action where one has to integrate over all these epsilons except for the -1, 0, and 1 modes. So as temperature goes to 0, these modes become more and more important. Good. So what happens if we integrate out these modes? Well, we get the partition function of a black hole close to extremality. So at leading order, the answer for the partition function of a black hole is just given by its entropy, S0. Here, S0 is proportional to the charge of the black hole squared. Then if you compute the one-loop determinant from all the fields and account for the dependence of the previously shown, of the measure of the previously zero modes on Q, you get this, lovely factor of the log of Q, log of the area, that Sen and collaborators computed. Here, NS and V and NF are the number of free scalars, vectors, and fermions and that couple to gravity. But in addition to that, you get this factor which goes, that come from the modes that were zero modes at exactly extremality, that goes like a factor of t to the 3/2. And this becomes extremely important at low temperatures because notice that as the temperature goes to 0, the partition function itself goes to 0 instead of going to an extremely large number. So the moral of the story is that these near horizon modes cause large quantum corrections at small temperatures, and that you could explicitly see by looking at the density of states of these black holes. So you just take a Laplace transform of the formula for the partition function that I was telling you. So here it is. Here is what the Laplace transform would look like if you neglected the contributions of these modes, if you just assumed that the integral over these modes gave you a constant that's temperature independent. So it goes to a very large value at extremality. And here's what happens if you include these modes, namely the density of states goes towards 0 at extremality, and it starts deviating from the previous semi-classical computation at precisely the breakdown scale that Preskill and collaborators discussed in the 90s. So you could also look at how the new energy above extremality behaves with the temperature. That's the plot that I showed you previously that seems to cause a lot of problems. And using the new density of states, you find that the energy above extremality always behaves like 3/2 times the temperature. And that 3/2 came from the number of, absent modes that we didn't integrate over, which was related to the isometry group of the near horizon geometry. Okay. Nevertheless, to fully understand the puzzle of the thermodynamic breakdown, we really have to discuss what happens to the Hawking radiation itself rather than to the partition function of the black hole. So if you were a faraway observer from these black holes, how would you see this breakdown? Or would you see it? Would you see large quantum corrections? So for that, we will answer the following questions. One, how close do we truly get to extremality? So previously it seemed that we were getting exponentially close, but is that really true? Two, how is the spectrum of neutral radiation affected by these quantum gravity effects? And how is the particle pair production rate affected? And from all these answers, we will derive the full evaporation history of such black holes. So let me start with the easy case. It turns out that the evaporation of neutral particles is not that hard to do. So for that, we just have to take the previous calculation of the partition function and consider the response of the black hole if I send an incoming wave from infinity. And when we send an incoming wave, what we'll compute is the stimulated emission rate from that black hole, and using the techniques from early days of quantum mechanics, we can compute the actual, full emission rate for neutral particles. So we consider an incoming wave coming from infinity, just for simplicity of a massless scalar that has some angular profile with some angular momentum L. And we send it into the near horizon region, and we want to understand how this wave couples to the modes that we were discussing previously, that were the strongly coupled modes that glued the near horizon region to asymptotic infinity. So effectively, what one needs to do is modify the Schwarz in action, that's the effective theory of these modes, by coupling some operator, some simple operator, that couples to the value of this wave along this line. The value, the wave equation can be explicitly solved in this region, and you find that close to this blue line, it takes the following form, where z boundary is the Poincaré coordinate in ADS2. And from this value of the four-dimensional metric, of the four-dimensional value of the scalar field, you could extract what this coupling that appears in what the source for this operator is. You could extract what this phi 0 is. So namely, you see that it scales with powers of R plus and E breakdown, and R plus modified by the frequency of this mode. So the important thing to keep in mind is that this number is a very small number, because R plus scales with the charge and E breakdown scales with 1 over the charge to a cubed. And this number is a very small number because we are working at very small temperatures, so the frequencies of Hawking radiations that could get emitted are also very small, so omega times the charge of the black hole is extremely tiny. So because this phi 0 is so tiny, we can just apply Fermi's golden rule to compute the transition rate. And that Fermi golden rule just depends on the two-point function of this operator O that describes the effective coupling of this wave to the near horizon region. And the nice thing is that correlation functions in this Schwarzian theory are known exactly. They were computed in this paper. And this allows us to compute the transition rate explicitly for any initial energy. This EI is the initial energy of the black hole, and EI minus omega is the final energy. So from this, yes? Is this? No. So let me just tell you the notation. Sorry, by this point it became standard. This plus minus means a product of 4 gamma functions with all possible signs. My bad. I didn't want to write 4 copies of that term on the slide. So, for instance, for a neutral scalar, if we have a massless scalar, the majority of radiation comes from the S wave sector, and we can explicitly write down what this gamma function just takes a very nice form for any energy, just because L is set to 0. It takes the following form. This is the Schwarzian corrected distribution in terms, the Schwarzian corrected spectrum for a particle. And this is just the gray body factor that came from the wave equation that tells you how difficult it is for this neutral particle to escape the near horizon region. So this is the exact calculation, but if we take initial energies that are much larger than the breakdown scale, we precisely recover the semi-classical answer that was known, since Hawking. We recover that the answer is given by the Bose-Einstein distribution times the gray body factor. So let's just compare these 2 calculations, the exact one and the QFT on fixed background. If we start sufficiently far away from extremality, so 100 times the breakdown scale, you see that the energy emitted per unit time, per unit frequency window is kind of similar between the quantum corrected answer and the answer that comes from doing the QFT on a fixed curve background. However, if we go below this scale, so let's say that the initial energy is 1/10 the breakdown scale, this is the quantum regime when the JT modes become important, the semi-classical distribution becomes completely different than the quantum corrected one. And this is what resolves the puzzle that I was showing you previously. Namely, semi-classically, you emit particles with much higher energies than you do when you include quantum corrections, and that's why you could seemingly go below extremality. Here, the calculation explicitly shows you that you cannot emit a particle with energy bigger than the initial energy above extremality, which makes sense. So, we can compute the evaporation rate into massless scalars. Here is the microcanonical answer. So essentially, the answer changes from being a power law to having a different power in the initial energy. And we can also do it in the canonical ensemble. And I just wanted to point out something on this slide that might seem confusing. Namely, you see that the power of the initial energy is smaller when you include the quantum effects. It's squared versus 7/2. And that doesn't happen in the temperature case, but that's also because the relation between the energy of a black hole and the temperature of a black hole changes when including quantum effects. It goes from the energy being quadratic in temperature to the energy becoming linear in temperature. So it's a bit better to think about the setup in the microcanonical ensemble. So this is for massless scalars. We also computed it for photons with all the gray body factors. Once again, you get a change in the power law. And we haven't fully computed the gray body factors, but are almost there for gravitons. And the curious thing is that they have the same scaling of the energy above extremality as the photons. So basically, the black hole, the dominant evaporation channel in our own world, is a combination of the photon and graviton field. And here it's actually a bit more subtle. These are not just pure photons. They're a linear combination between electromagnetic modes and some modes of the metric. Okay, but this is the story for neutral particles. Any questions? Yeah, it's because, roughly speaking, the equation of motion slightly changes, and it's kind of a coincidence that you end up with the same scaling. I don't fully understand why the gray body factor ends up being the same. It's just what the calculation spits out. Sorry? They're not suppressed. Because we don't have a massless scalar. This was just for example purposes, as far as we know. Okay, good. So how about the evaporation rate into charged particles? How do we resolve the previous divergence that I mentioned? The Swinger pair production rate for charged particles can be computed by going to Euclidean signature. So this is again Euclidean ADS2, and finding instanton configuration of charged particles and computing the new partition function in the presence of these instantons. So it's a very old calculation. And the trajectories for world lines of charged particles were actually found by Compet in the 80s. And they're basically given if the mass of the particle is less than its charge. They're given by circles in ADS2. Good. But this circle, since ADS2 is homogeneous, doesn't have a preferred location. So that's where the volume factor came in, right? We have to integrate over all the possible positions of this circle, and that's a zero mode of this instanton configuration. So the question is, do these translational modes get lifted? And one way to understand these translational modes is that the SL2R isometry of this space-time gets broken by the fact that we insert this circle. So namely, two of the transformations of SL2R, two of the free generators, get broken because we have a preferred location where we put this instanton. One of them is are just the rotations around this instanton configuration, and that gets preserved. And the fact that the symmetries get broken means that these large diffeomorphisms that now exist in the near horizon region are actually physical. If I do a large diffeomorphism that corresponds to one of the naive SL2R isometries, I can change the location of this instanton relative to the boundary. So now it means that from the perspective of the gravitational path integral, I actually have to integrate over these modes. They're no longer isometries. So I have to take the previous expression that I saw previously and also integrate over the n equal 1 and -1 modes, which were previously thrown away because they were corresponding to isometries. And you can see that in this action, the weight of these modes are 0. So I actually have to do an integral over 0 modes, which is problematic. However, there's one thing that I've neglected in this computation, which is I've neglected to include the back reaction of the instanton on the space-time. And if you include the back reaction of the particle on the space-time, the space itself is no longer homogeneous. So you not only break the SL2R isometry related to where the particle is, you actually break the SL2R isometry for the metric itself. So we expect that when we include back reaction of the particle on the space-time, this should give weight to these modes and affect the Schwarzschild perturbation theory that I described earlier. Okay, so does that happen? Well, we try to find this instanton in a general setting, not only close to extremality. We try to find the back reacted geometry for any mq little m little q, and we managed to do that. So we take the following action, which is the Einstein-Maxwell action, coupled to the world line of an electron. And we try to take our initial geometry and now find a new geometry. And the new geometry has the following features. These parts, each part of the space-time is described by a smooth Reinster-Nordström metric that has to be glued across the path of the instanton. So to describe this metric, it's useful to have in mind 3 temperatures. There's the temperature of the thermal circle on the outside. That's given in terms of the mass m and q of your black hole. There's the temperature of a Reinster-Nordström black hole on the inside. This is the temperature after the instanton is emitted. That's given in terms of the new mass of the black hole and its new charge. And there's another temperature, which is the Reinster-Nordström temperature in terms of the same mass m and q in the absence of the instanton. And the reason why these 2 temperatures are different from each other is because usually to determine the temperature of the black hole, we have to impose smoothness at the Euclidean horizon. So you take this geometry in the absence of this instanton, this geometry should be smooth at the Euclidean horizon, and this gives you t as a function of m and q. But there's nothing that tells us that this outside geometry should be smooth at the Euclidean horizon because that geometry doesn't include the Euclidean horizon. And in fact, it's not. If you continue this geometry past where the instanton is located, you get a small defect at the location where the Euclidean horizon would be. And the opening angle of that defect is related to this parameter alpha by the defect angle being 2 pi alpha. Okay, so our goal is to find this instanton configuration, find all the temperatures and all the masses, and we've explicitly done that. And here are some properties of the solution. I won't. The solution itself is quite ugly, but it has a few very cute properties. So first, the solution itself only exists in a certain range of charges, which then this range of charges is slightly different from the weak gravity conjecture. This range of charges tells you that instead the charge of the particle needs to be bigger than this quantity, which itself is bigger than the mass of the electron. So that doesn't mean that particles that don't satisfy this bound don't get emitted. They just don't get emitted through this non-perturbative process of Zwinger pair production and are actually further suppressed. The area of the instanton is incredibly small. If I take the area of the instanton and divide it by, measure it in units of the ADS2 radius, it's suppressed by factors of m over q. and by q times t. So when I take the black hole very close to extremality, these instantons become extremely tiny. So I can put a lot of them in the near horizon region. Free, we can determine the angle alpha of the defect explicitly. This is its analytic form. And it's very close to 1. And it's also suppressed by factors of m over q. The fact that it's very close to 1 is a sign that the back reaction is very small. If it were exactly 1, it would be as if I would continue the spacetime on the outside and I would obtain a smooth geometry. For the mass of the, this is something that I found quite unexpected, the new mass of the black hole after the instanton is emitted is actually still very close to extremality. So naively, you'd think that the new mass of the black hole would just be the difference between the old mass of the black hole. So let's say that we're extremely close to extremality, so the old mass was exactly q, minus the mass of the electron. But the answer turns out to be much different than this, exactly because you can see here, because m is very different than q. It's almost as if we emitted a particle that doesn't take us away from extremality. It only takes us very slightly away. And this means that the electron, when it comes out at the asymptotic boundary, it's actually extremely highly relativistic. It has an incredible energy, and that comes from the fact that after it was pair-produced, it got accelerated by the electric fields of the black hole in an extremely long throat, and when it gets spit out, it has this relativistic mass. So it's actually kind of close to the Planck mass. Yes? No. So the geometry that I discussed previously is perfectly smooth. The conical defect that I mentioned is just a useful tool that you'll see its purpose in a second. No, I don't think so. Well, if you like thicken the electron a little bit, the stress tensor won't be divergent on that world line. Okay, and 6, a new action of the instanton plus black hole configuration actually takes a very cute form. It's the new area of the black hole plus 1 over the temperature times the new mass, so times the old mass of the black hole. And this is something that's kind of a bit unexpected. We just computed the action explicitly for this metric configuration. So this is not obtained on thermodynamic arguments. I won't show you the exact expression because the new area of the black hole is slightly ugly, but I can expand this action in terms of the temperature of the instanton at low temperatures, since I want to be close to extremality. And what you find is that these were the old terms in the action. This was just the extremal entropy. This is the new terms. This you could think of as the actual action of the instanton, and this you could think of as the effect of the back reaction of the instanton on the geometry. And for the experts in the room, remember that previously this alpha was 1 in the absence of the instanton. So now it gets corrected. Instead of going like 1 over beta times q cubed, it goes like q cubed times alpha squared times beta instanton. And for those of you that have worked with JT gravity, you'll recognize this as the action of JT gravity in the presence of a defect. So you're precisely seeing the defect from the outside perspective. You're precisely seeing the defect that the outside region is seeing at the fake Euclidean horizon. Okay, so the action itself doesn't get changed much. So the most important role of this back reaction, as I kind of hinted at earlier, is to lift these translational zero modes. So we can again look at the perturbations of the metric now in the fluctuating around the instanton configuration. And instead of finding the old action that had at quadratic order that had n squared times n squared minus 1, we now get this angle, alpha, appearing in the game. So the modes that were previously exact zero modes that we had to integrate over, epsilon 1 and epsilon minus 1, now actually get a non-zero weight, which means that we've essentially regularized these modes. They now have a finite contribution. So the new partition function of a black hole plus one instanton takes the following form. This answer is completely independent of the temperature of the black hole. So this, again, you could think about as the instanton action, and this is its one-loop determinant that doesn't actually include the fluctuations in the position of the instanton relative to the boundary. That's because we've already included those fluctuations in fluctuations of the metric. They're the modes epsilon1 and epsilon minus 1. And they produce a gravitational one-loop determinant, which now no longer has a power of 1 over beta to the 3/2. It has a power of 1 over beta to the 1/2. That's because the SL2R isometry got broken to U1. And this is the new classical gravitational contribution of the action when including back reaction. So from this, we can already extract the leading order answer for the new pair production rate. We just take the ratio between the partition function of black holes plus any sum of instantons divided by the partition function of the black hole. And this should reproduce e to the I gamma beta, where gamma is the pair production rate. Now, we've only included so far a single instanton, so we should only compare this answer to the expansion of e to the I gamma beta. So we should compare this to this term, which is the ratio of the partition function of one instanton to the black hole, and we find this answer, which is completely finite and is perfectly consistent with this factor of beta gamma because it's linear in beta. So the fact that the Schwarzian gave a different one-loop determinant in terms of its temperature is no coincidence. It's precisely to get this factor of beta that produces the right scaling to obtain the pair production rate. And this pair production rate is now finite, even at extremality. It's a perfectly fine result. Good. However, there's still a puzzle. To fully compute gamma, we actually need to understand how to sum over all instantons and how that sum resums into e to the I gamma beta. Right? This is what we typically do for instantons. We have to resum them for the pair production rate to appear in the exponent. And this is typically true in the dilute gas approximation, when the instantons don't interact with each other. So the question is, does this dilute gas approximation work at the level of the gravitational path integral, or are there further problems? And you'll see I'm not talking about gravitational interactions. I'm just talking about a count of the moduli space of instantons itself. So the reason why one should be a little bit worried is that the moduli space of instanton, if you put all these instantons in the near horizon geometry, each instanton produces, from the outside perspective, if you're not not inside of the instanton, each of these instantons produces a little defect. So we can think about the moduli space of instantons as being the same as the moduli space of conical defects in the near horizon geometry. And we have to resum these moduli space. So this is what zk defect is as a function of beta. It's the partition function in the near horizon geometry in the presence of k of these defects, where each of these defects carries a weight that's given by the instanton action. Now, this moduli space of conical defects is something that's pretty subtle to compute. Partly because in the gravitational path integral, we have to quotient the integral over metrics that captures the positions of all these instantons by the space of all large diffeomorphisms. And here, I mean large diffeomorphisms, discrete ones, not the ones that don't vanish at the boundary, the ones that correspond to elements of the mapping class group. And these geometries have non-trivial mapping class group. So it would actually be very non-trivial if the partition function with k defects would be precisely produce the right factors such that everything resums to an exponential that's proportional to beta. And there's even a subtlety, even if we produce this factor of beta times e breakdown to the k associated to each instanton, this is not actually the dilute gas approximation, because in the dilute gas approximation, these would be factors of the volume. This is not actually the volume of the space-time, because as we saw, it got regularized even for one instanton. So the question is, how do we compute the sum over such blunt defects to obtain the moduli space volumes? And one issue is that people, yes? Yes, yes, yes. So when you put these instantons in Euclidean signature, right, because they get spontaneously emitted, they should correspond to some instability of your system. And this I to the k is precisely such that it would resum to e to the I gamma beta, which should give you an imaginary shift of the energy levels. And that imaginary shift corresponds to the instability and gives you the decay rate for each individual energy level. So this I to the k came from the fact that these instantons actually had one mode whose eigenvalue was negative. But this is like something standard that people discuss in metastable systems. All right, so how do we compute the sum over such defects? In principle, one might think that one could use these moduli space volumes of Riemann surfaces, which were used before, for instance, in the work of Douglas and collaborators. However, one does not actually have a formula for those volumes for very blunt defects. The reason why is because those volumes are computed by cutting out these Riemann surfaces on a closed geodesic. And these geometries actually have no closed geodesics that separates the asymptotic boundary from this gas of defects. We'll see that actually when we resum these defects, we obtain a slightly different result. It will be close, but slightly different. So the way to actually resum these defects comes from the duality between JT gravity, which captures the weight of these defects, and the 2 comma p minimal string at large p. So as you might have heard in previous talks in the week, JT gravity and this model are believed to be dual. And JT gravity with blunt defects, it has been checked in these papers, that it's actually dual to the 2 comma p minimal string when you turn on some tachyonic deformation of this model. And the density of states in this theory is related to the string equation in this theory, where the string equation can be written as the terms of the KdV couplings. And the density of states takes this very simple form. What we're actually interested in is not the entire density of states. That will be a subleading effect. We're interested in the spectral shift, right? We saw that what we want to obtain is gamma, and gamma is the imaginary part of minus the imaginary part of the spectral shift. And there will also actually turn out to be a real shift to E naught, which corresponds to a slight change in the extremality bound of these black holes coming from non-perturbative effects. So to determine the spectral shift, we just have to solve the string equation in this model and then solve this equation for the string equation. Okay, so the authors that I previously mentioned actually solved the string equation in this model, and it takes the following generating form. That's explicitly given in terms of the weight of the defects, which in our case are just the action, the e to the minus, the partition functions of individual instantons. You could solve this equation, so we want to solve this equation is equal to 0, in a perturbation theory, let's say in the angle of the defect. This angle is very close to being very blunt, so 1 minus alpha is very, very tiny. So we can solve for the spectral shift in this perturbation theory, and beautifully, at leading order, we get exactly the expected result, as if like we're resumming independent instantons. So this is the analog. It's the moral analog of the dilute gas approximation. But we get higher and higher order corrections, some that are real, like this one, and some that are complex. Actually, even powers in e to the minus I instanton turn out to be real, and odd powers turn out to be complex, which means that these odd powers are the ones that produce a shift of the pair production rate, and these even powers are the ones that produce a shift of the extremality bound. These are very, very tiny shifts, but nevertheless they're interesting. They come from the previous effects that we've seen in this talk came from perturbative quantum gravity effects. These types of shifts of gamma come from non-perturbative effects. I'm not exactly sure whether one should actually, I'm sure that we should trust this shift. I'm not sure how it competes with other corrections to the Swinger pair production. But this leading order answer, which I again want to emphasize is had to be regularized through the gravitational path integral, is still very good to get. So there are also corrections to the entire density of states of the spectrum. Rho that I showed you earlier changes a little bit in shape, but those are further subleading in this 1 minus alpha expansion. And from this answer, I want to also emphasize we can also extract the pair production rate for smaller black holes, namely when we approach this line when the black hole has approximately 10 to the 44 charges. And in that case, you have to resum the entire instanton series because the weight of each instanton, which is given by its action, goes to 1. It's the regime in which I instanton goes to 0. So you really need to resum and make sure that you correctly accounted for the one-loop determinants around each instanton configuration. And you obtain this rate, which is extremely large. So as you approach this line, the pair production rate goes from being exponentially suppressed to being hugely enhanced. It's a bit like past this line, you kind of super radiate these charged particles. Okay, so with that, let me present the evaporation history of a charged black hole. We start at this point, as I described, semi-classically, we start decaying for a while. The Hawking radiation as a function of time makes the log of m minus q naught go like minus a quarter time. So this is the semi-classical result. And the semi-classical result is valid up to this breakdown scale. And past that, we had to include perturbative corrections for the neutral particles, and the power law changes as a function of time. You get this new coefficient. And when you reach exponentially small temperatures, exponentially in the instanton action, below extremality, you radiate 1 electron or 1 positron, depending on the charge of the black hole. This actually takes you above the breakdown scale quite considerably. So you again end up in the semi-classical regime, radiate for a while. Again, quantum corrections become important for the neutral radiation. And the process just repeats itself over and over again at time intervals of order the pair production rate inverse. So you stay very close to extremality in this tiny band up to the point where the instanton action becomes close to 0. And at that point, you just radiate charged particles at an extremely fast rate. So yeah, this is what this process is showing. And the factor of gamma can be computed now by resumming all our instantons. So to summarize, charged black holes with large enough charge get incredibly close to extremality when left to evaporate in vacuum. Close to extremality, quantum corrections drastically affect the rate of Hawking radiation for both neutral and charged particles. We can now systematically compute these corrections and predict what an observer far away from the black hole would see. So instead of computing prediction functions, we're now actually computing spectra of particles. And let me just discuss 3 possible connections. One is a connection to the weak gravity conjecture. So the initial motivation for the weak gravity conjecture is actually very much related to this problem. It came from the fact that if we only had neutral particles in our universe, or you don't have particles that satisfy the weak gravity conjecture, we would be forced to go towards extremality and be left with an extremal black hole that carries extremely large entropy. It would be a remnant, essentially. In our calculation, that's no longer true. Perturbatively, at least, we see no problem in the absence of charged matter or in the absence of matter that doesn't satisfy the weak gravity conjecture. You just keep radiating down in the spectrum all the way up to extremality, but at extremality you no longer have an object that has a very large entropy. You probably end up with a single stable state that just survives forever, but it's a single state, so it shouldn't be a problem. So perhaps this suggests that one needs to look deeper for motivations for weak gravity conjecture at non-perturbative corrections in e to the -1 over g Newton, such as the wormhole corrections that were used for the violation of global symmetries. The second point that I want to make is for BPS black holes, the density of states itself looks quite different. It has a gap, as you might have heard earlier this week. And the fact that it has a gap probably hugely changes the calculation of Hawking radiation, even for neutral particles. Namely, if you end up very close to extremality here, and you radiate neutral particles, you should somehow see that you will only emit particles that have this energy, the energy given by this gap. So I suspect that if you do the calculation for BPS black holes, you should actually see this gap as a spectral line in the Hawking radiation, just like we did for the hydrogen atom. Finally, it would be interesting to redo this calculation of pair production for near-extremal Kerr black holes and see what happens in that regime. Here, the particles that are charged are the particles that carry angular momentum. And they're charged under essentially a non-abelian field that is part of the black hole metric. And the question is whether in this pair production rate, the pair production rate can be seen as computing the super-radiance rate very close to extremality, including quantum effects. So yeah, this near-extremal Kerr geometries, the perturbative quantum gravity effects on the partition function were discussed in these two recent papers, but I think it would be interesting to redo the calculation for Hawking radiation. All right, I'll end it there. Thank you very much.
Being confused, but could you show us this slide about the diagram of the evaporation history of the black hole?
This one?
Yeah. So you say that when you emit electrons, the mass actually goes up.
Oh no, probably.
It should go like very close to horizon.
It goes probably.
It should go
like
horizon. You should take like the 90 degree.
It reaches this line like this.
Yeah, this looks very good. I mean, you shouldn't gain black hole shouldn't gain mass by emitting radiation, right?
Well, in fact, it was in this formula for m bar.
Yeah, I think that one's correct, smaller. But I think that diagram is very misleading.
Sorry about that. Sorry about that. I agree with you. Thank you.
Thanks for a great talk. So Schwarzschild is actually one loop exact. This is why you can trust this T to the 3/2 all the way to very low temperatures. But when you add instanton, you are deforming away from Schwarzschild.
Well,
can you trust this one loop to?
Yeah, the fluctuations of these modes. So there's two type of fluctuations that we consider. One is for the shape of the instanton, and the other one is for these modes at the asymptotic edge of ADS2. And these two fluctuations kind of decouple from each other. So I think I would still trust this result of 1/t to the 1/2. And in fact, the one loop the fluctuation of the shape of the instanton is also one loop exact. Because of the homogeneity of the space. So yeah, I think the calculation is fine. As in, yeah, I have no more to say than that.
Okay, thanks.
So is there a possibility that instead of these particles flying to infinity, they will form some condensate?
I don't think so, because they just get accelerated out. So what would stabilize them?
A quartic coupling, when you increase the occupation number, some 5⁴ can lead to some kind of hair. It's like a hair.
Oh, I see what you're saying. I think that might be happening. I'm not exactly sure, but I kind of have the suspicion that these examples of instabilities of charged black holes in ADS are related to that. I suspect that if you do the calculation there, when you get a very large decay rate, you'll get a very large decay rate close to extremality, and the pair production can be viewed as condensating the scalar that under which these particles were charged. But in the regime in which this Schwinger pair production is exponentially suppressed, I don't think that can be the case. I think actually there is a paper by Sachdev and Hartnell that tried to make this connection, but I haven't looked that much into it. Oh.
All right, so let's thank Luca again.
Thank you very much for the comment.